All right, so now we're going to look at the directing abilities of substituents, and we're trying to make arguments for why something is a meta-director or why something is an ortho-para-director. So to understand this, you have to look at the intermediate. And how does the substituent affect the energy of the intermediate? So things that we'll look at are, does the group that's already on the ring make one or more resonance structures in the intermediate especially stable? Or is there an extra resonance structure in the intermediate? As you know, if you increase the number of resonance structures, you spread out the electrons, you lower the energy. Or is there, because of the substituent already on the ring, is there an especially unstable resonance structure in the intermediate? So let's look at alkyl groups. We have alkyl groups, and these are ortho-para directors. You can add, we'll consider nitration. We can add a nitro group ortho, meta, or para to the methyl group already present on toluene. And the intermediate for all three of these contains 3 resonance structures. But we see that when you add ortho, or when you add the nitro group para to the methyl group, you get an especially stable carbocation intermediate. And why is that extra stable? Because that's a tertiary carbocation. The rest of these structures are secondary carbocations. And you do not get this extra stable resonance structure when you add meta. So if we were to look at the reaction profile diagram, we could proceed to the ortho or para intermediate, or we could go to the meta intermediate. And the meta intermediate is higher in energy because it does not have this stable structure. The ortho intermediate or the para intermediate is lower in energy because of this more stable resonance structure that's in the mix of resonance structures. We do not see that in the meta. So the intermediate is lower in energy. That impacts the transition state energy. It makes the activation energy lower to go to orthopara, makes the reaction rate faster. So you can see here you do get some meta, but that reaction is going more slowly than the reaction heading to ortho or para. Now, if you have groups like hydroxyl OH or NH2, these activating ortho-para directors, we can look at the intermediate once again. And the first thing you see is that if you go ortho or para, you have an extra resonance structure in the intermediate. 4 structures. Here you only have 3 structures. Where does that extra structure come from? Well, when you have the carbocation located right here, there's a possibility to move the lone pair electrons from the oxygen to form a pi bond to that carbon. And that only occurs when you have an ortho attack or para attack. It does not occur when you have a meta attack. So you do not get the extra structure. So the extra structure lowers the energy, but not only that, but that extra structure is extra stable because all atoms have an octet. And that is especially stable. We do not get that in the meta edition. Now halogens are deactivating, but they're ortho-para directors. And remember, when we're considering directing ability, ortho-para versus meta, we look at the intermediate. So regardless if it's activating or deactivating, the lone pair on the chlorine, like on chlorobenzene, or if you had a bromine there, acts the same way as the lone pair on an oxygen. What does it do? It gives us an extra structure in the intermediate that is especially stable. So if there are electrons on the atom bonded to the carbon of the ring, that will make it an ortho-para director, regardless of whether it's a deactivator like a halogen or an activator like an oxygen. Finally, deactivating meta-directors like an aldehyde and benzaldehyde. These are meta-directors, and the argument for why they're meta-directors is just a little different than for the ortho-para directors. We have three resonance structures, whether it goes ortho, meta, or para. But we have an especially unstable structure. And the reason why is because this carbon has a slightly positive charge. And when you try to add the new group, nitro in this case, ortho or para, you end up putting a carbocation in one resonance structure right next to that carbon. That does not occur when you go meta. So the explanation here is that adding a group in this mechanism, ortho or para, produces a resonance structure that raises the energy of the intermediate and makes the reaction, and therefore the transition state, and makes the reaction go more slowly. We do not have that unstable structure for meta addition. So with the meta intermediate, is lower in energy than the ortho-para. Intermediate. And it's not that the meta intermediate has some extra stability, it's that the ortho-para intermediate has some instability to it. So we've just seen that groups like these are activators relative to benzene because of electron donation, either inductively or through resonance. Halogens are deactivators because while they can donate through resonance, the inductive effect is very strong. And then these are deactivators because of a positive or slightly positive charge on the atom bonded to the carbon. The activators are all ortho-para directors because the ability to donate electron density stabilizes the intermediate formed when you have ortho or para addition. Halogens are deactivators, but they are ortho-para directors. Why? Because of their lone pair. In the intermediate, despite being deactivators, once the reaction goes, those lone pairs provide a way to stabilize the intermediate if you have ortho-para addition. And the deactivators, other than halogens, are all meta-directors because the ortho-para additions have intermediates that are especially unstable because of one of the resonance structures. So the line dividing OP directors versus meta directors is here, and here we have activators and deactivators. And so all activators or ortho-para directors and all deactivators are meta-directors except for halogens.